Hello everyone, welcome to Unacademy. So guys, this is another practice video in which I am posting some good questions, and I hope that this is going to be beneficial for the IIT JAM students, CSIR NET aspirants as well as GATE aspirants, guys. So yes, I want you to focus on this point that without crossing the basic level you cannot clear the CSIR NET exam also. So you have to see questions from everywhere, from IIT JAM, also from your CSIR NET and GATE as well. So yes, here are some good practice questions from IIT JAM. So most of the questions, all of these are from paper 2020. Okay. So yes, let's talk about these questions. So I hope that you will try them by yourself first of all. So the first question is, the correct order of boiling points of the compound from 1 to 4 is. So actually this is just a 1 mark question and a very important question, because see, order of boiling points here it's just going to depend on branching, right? You first of all sorry, so all of these four options, 1, 2, 3 and 4, you see, only option number 2 is going to be an ether. All of the other ones are your alcohol. So based on the structure of alcohols because of hydrogen bonding give you a greater boiling point. Now greater the branching, lesser is the boiling point, and that is why what happens is one is going to have a maximum packing and maximum boiling point, then goes your 3, then goes 4 because it is having maximum branching, then lastly comes 2. So your answer is 1 greater than 3, greater than 4, greater than 2, and this is based on hydrogen bonding as well as branching, both of these concepts together. Okay, easy question. Another good question is, the d orbitals involved in the hybridization to form the square planar as well as trigonal bipyramidal geometries are. So this is a very logical question from you all. So basically how can you think about this question is, it's very easy. So respectively is given, and that you is what you have to focus on, right? So what you can do is, first of all if you want to see the square planar geometry, where is it coming from? It is coming from removing, square planar geometry is coming from removing the ligands on the z axis, right? So if you are actually able to understand that concept, that if you remove the ligands from the z axis, the only ligands which are remaining will be on the x and y axis only, right? So x and y axis ligands you are keeping and the z axis ligands you are removing. So which axis will be used? Definitely dz square minus y square from the metal itself to interact with the remaining ligand that you have got on the square plane. Okay. Similarly, so if you are talking about octahedral conversion to trigonal bipyramidal, octahedral conversion to trigonal bipyramidal. Now you see that one of the ligands which is removed is from the x and y axis. From here one of this ligand is removed, let's say. So what is the orbital which is going higher in destabilization? Which orbital is going higher? That is going to be dz square for trigonal bipyramidal, right? So the involvement of dz square is greater in your trigonal bipyramidal geometry, and in your square planar it is dx square minus y square. So your answer is option number C. Moving onwards, you have another good question, that is the major product formed in the following reaction sequences. Now guys, it's a very good question, and also it is a name reaction. So first of all we are going to talk about this ethyl magnesium bromide, and I think it's only 1 mole over here. Why 1 mole? Because you just have to convert the keto into an alcoholic group. So let's say this is your ethyl over here, it is your OH and the double bond. Now you have a allylic alcohol system. So in the second step it is your chromic acid, chromium oxide given over here, CrO3. So chromium oxide is basically supposed to do oxidation of alcohol, but you see that this alcohol does not have a proton on the same carbon. How is the oxidation going to happen? So the intermediate, this is going to undergo rearrangement like this. So first of all your oxygen and chromium bond is going to form as always, that forms for all the other species. It is going to be like this, O minus. And because the oxygen of the chromium cannot take away a proton from here, it is going to give you a rearrangement like that of a 3,3 sigma tropic rearrangement, very similar to that. And this is what you get now. So your double bond has actually shifted in position. Oxygen comes over to this carbon now. This is O minus once again. Now this O minus is going to take away this proton available on the other carbon, and this is how the rearrangement, this is how the oxidation happens basically. So your product is going to be like this. ये देखो, this is your oxidation product. So your product is going to be this is double bond O over here. So your oxidation happens not directly but through rearrangement. Alright, so why does it happen, guys? But because this is a tertiary carbon. Tertiary alcohol cannot be further oxidized, but it will be oxidized if it is your allylic tertiary alcohol, and it is going to undergo rearrangement and further oxidation like this. Now in the third step you have a simple Wittig reaction. Okay, you have a simple Wittig reaction which is going to, in the presence of this ylide, which is going to give you option number B as your major product. There is a ethyl group over here, the double bond on the more substituted side, and the CH2 connected over here. So you're getting answer as option number B. Rest everyone, all of them, there is something wrong. You are not getting oxidation. The position of the alkene is incorrect. You are getting an exo double bond. Okay, so B is our correct answer. Another good question I found is the order of metal carbon bond strength. So the same question could be asked in many different ways, right? So either I can ask you metal carbon bond length, or I can ask you bond strength, which is asked in the question. Bond strength is directly also proportional to bond order of metal carbon. Similarly, I can ask you carbon oxygen bond length, that is your carbonyl bond length, then carbonyl bond order, okay, and carbonyl bond strength as well. So the same question could be asked in so many different ways. Now what you have is, you have 4 examples, okay, 4 metal complexes in which you see that all of these are carbonyls, just that here there is 2 minus charge on the complex, and definitely guys, carbonyl is neutral, so the charge is on your metal only. It is your titanium 2 minus, here it is cobalt minus, manganese manganese positive, and here it is chromium 0. So basically when you are doing when you are having an excess charge on the metal, you know that the excess charge is going to do pi back bonding like this. Okay, and you are being asked the strength of the metal carbon bond. So you will say greater the pi back bonding, greater pi back bonding, greater is going to be the metal carbon strength, isn't it? So this is what you will say, metal carbon strength is going to increase when you have a greater negative charge on the metal. So it is titanium having the maximum metal carbon bond strength due to maximum pi back bonding. Then comes your chromium, and lastly comes your manganese like this. So your answer should be 3, 4, 1 and 2. 3 greater than 4, greater than 1, greater than 2. So this is your correct answer. The same concept is asked in GATE, is asked in CSIR NET as well. Another good question, guys. So basically the number of DD transition expected for this complex right over here. So what happens in this complex is, you are having copper 2 plus, okay, so copper 2 plus is your D9 system, and this is octahedral. So what you are going to write is, alright, so this is your D9 system. Now D9 system is going to give you 2D term, okay, because there is just one unpaired electron, and it is going to give you D term, okay. Now what happens is, when you are drawing the diagram, when you are drawing the orgel diagram, you see that a hole is transferring from the EG level to the T2G level. Yes, we consider it like that. So here a hole is, we are not considering that the electron is transferring, we are considering to define the spectra that a hole is transferring from the EG level to the T2G level over here, right? So looks like it is going to give you just one line, just one spectra. Number of DD transition looks like it is just one, but what happens is it is a D9 system. In the EG level there is electronic degeneracy or asymmetry of electron filling that causes jahn distortion. jahn distortion is going to make these levels split further into two different levels like this. So what is your transition now? One transition, two transition, three transitions. Okay, so you basically have three transitions. Now what happens is, this is your another E level, this is another T2 level, and both of these are A and B levels over here. So what happens is basically these three transitions are not very nicely observed because these are very small transition, very little splitting that you are going to see, although the answer is C over here. In the answer key it is C, but what happens is you see a broad band. You see one single peak. You are not getting three peaks differently, you are getting one single peak, and that is going to be a broad peak. Okay, because of the jahn distortion. Alright, so yes, the answer is C. Now we move onwards to another question. The plot showing the magnetic behavior of oxy solid line and deoxy hemoglobin dashed line is. So basically guys, looking at the molar magnetic susceptibility, basically oxy hemoglobin is going to be your Fe. Some books it is written Fe2 plus low spin. In some books it is written Fe3 plus low spin. Alright, both of these are actually correct only. Now when they are low spin, they are actually going to be in your hemoglobin. You know that it is your the overall molecule, the overall magnetism is going to be anti-ferromagnetic coupling that happens, right? So that is why you are not going to get these graphs. Okay, you're not going to get these graphs. One of these may be correct. Now what you see is the solid line is for the oxy molecule over here, for the oxy hemoglobin over here. So oxy hemoglobin is there in the low spin. It is having minimum paramagnetism. It is showing you minimum paramagnetism. So it is the line, the solid line is at 0, and in the deoxy form there are more unpaired electrons, and that is why the dashed line is at 3. So you don't have to exactly find out what is the value, you just have to see the bold and the dashed line. That is a very simple question. Answer is option number A. Oxy is there in the low spin and deoxy is there in the high spin. So that is why there will be greater number of unpaired electrons over here in the deoxy. This is just what you have to see. Okay, easy question. Now you move onwards to question number 25 over here from the 2020 paper itself. The major product formed in the following reaction is. So if you have done this question, it is super easy. Very basic question from the Favorskii reaction. So you have a methoxy over here, and yeah, what usually happens in the Favorskii reaction is one of the alpha proton is removed, and on the other side you must have a halogen to be removed, so that you get a cyclopropanone intermediate like this. Now the cyclopropanone intermediate will be once again attacked by methoxy, and the bond is going to open apart in such a manner that you have the phenyl methyl carbanion. You have the carbanion on this position, okay, because it is more stabilized towards the phenyl side, and on this carbon you have bromine now. Okay, the negative charge is going to fall and it is going to make the Br eliminate. You have pH, methyl, double bond, and the enone system you have got. So this is your major product finally, right? A very simple question at that. And what you can see from here is, ये देखो हो क्या रहा है guys, in this option number A that you see, In option number A, both of the phenyl and methyl are on the same carbon, and that is how it is supposed to be. There is no rearrangement. Okay, the rearrangement only happens with when the cyclopropanone is opening up. All right. In option number B, it is wrong because phenyl and methyl are on different carbons. It is not a carbocation rearrangement, so it is wrong. Once again, option number C, you see phenyl and methyl on different carbons, wrong. And here the methyl has disappeared somehow, so it is absolutely wrong, right? Your answer is option number A, and it is your Favorskii rearrangement. Okay? Chalo, we move onwards to another one. The rate of solvolysis. Now the solvolysis questions are so important. They get asked in every competitive examination. Basic reaction mechanism. So let's look at the fourth one. You see that there will be a positive charge created when the bromine is leaving. So okay, let's make the positive charge on every system. So there is a positive charge over here. Yes, this is also going to leave positive charge on this 5-member ring now. And once again over here as well. So this question is actually the easiest out of all the solvolysis questions. Why? Because there is aromaticity included. Option number 3 is going to be very stable after losing the bromide. So I can actually say it is stable because of aromaticity. It is a cyclopropene system, right? So 3 is going to be maximum. Rate of solvolysis is going to be maximum. So we have two options which has 3 highest. Baki, it is wrong. So then 4 is going to be minimum. Why? Because it is becoming anti-aromatic after losing the bromide. So 4 must be minimum. That also you have in these two questions. Okay. Then next is, let's compare 1 and 2. 3, 4 comparison we have done. 3 is going to be maximum, 4 minimum. What about 1 and 2? So in the first one, guys, you are getting a carbocation on the bridging position. Even the delocalization won't help. So this is going to be less. Alright, and 2, it is your simple allylic cation that you are getting, okay, and also secondary allylic cation. So 2 is going to be better than 1. So 2 is greater than 1. This is your correct answer, option number C. We move onwards to another good question, that is more stable species in each pair of conformers are. You can stop the video, do it by yourself as well. So guys, in the first one, you see the first example that you see over here, you are having the tertiary butyl group in equatorial and here in the axial. Absolutely, this is going to be more stable. Why? Because in the axial, tertiary butyl group causes a lot of interaction, 1,3 diaxial interactions with these hydrogens. So 1 is more stable, I would say. Now, what happens in option number 2, example 2 over here, 3 or 4, which is more stable? Now, this has been asked in your GATE exam. That is, in option number 3, your methyl is actually causing repulsion with these two hydrogens. And in option number 4, you don't have methyl, you don't have a hydrogen because there is an oxygen. So I would say that okay, you can keep the tertiary butyl group on the axial position. Why? Why here can you put? Why not here? Because here there is no hydrogen to cause the 1,3 diaxial interaction. Here the little methyl group is causing more interaction as compared to the tertiary butyl group because of the lack of hydrogen. So 4th is more stable. Okay, that is because you're having the heteroatom without no hydrogens. Okay. Yes, and the lone pair will not cause repulsion because the lone pairs are very close to the oxygen itself, right? So they're not causing repulsion. About the third example over here, 5 is once again going to be more stable than 6. Why? Because you can make, you can write the hydrogen in this way, which does the hydrogen bonding with both of these oxygens, even though it is axial. So on the axial position, only hydrogen bonding is possible. On the equatorial, it is more stable conformation, but there is no hydrogen bonding. So once again, I would say 5 is more stable. So 1, 4 and 5. 1, 4 and 5. This is going to be our correct answer for this question. Moving onwards, you have another good question, that is major product formed in the following reaction sequences. So many times we have already done this. TiCl3 in the presence of copper and zinc, that calls for the McMurry coupling. It is your simple McMurry coupling reaction. and what you are supposed to do is you are supposed to make the E alkene out of here, because that is actually less hindered. So it is a single electron transfer mechanism. We are not going to discuss all of it, but yeah, you will know that this is how you are actually supposed to make a E alkene over here. Okay, OMe over here, and one carbon another attaches to another similar carbon, and you will have OMe and a phenyl like this. Now in the presence of HCl in the second step, what could you do is you can only hydrolyze the enols. Okay, just like this, you can only hydrolyze the enols like this, and your product is supposed to be having a double bond oxygen, because the oxygen will have a positive charge. Water is going to attack over methyl, the bond is going to open up. So you are actually supposed to have, I'm directly writing guys, there will be double bond O and pH. So your product would be option number D. Yeah, let me also see. No, here you're not having option D, because there is one carbon difference. Yes, just be careful about this. Okay, so there is not going to be any carbon difference exactly on the same carbon, that is your methoxy. Here only the hydrolysis is happening. Hydrolysis happens in the second step guys, not in the first step, because first step you are having the coupling, second step you are having hydrolysis. So your product is option number C. Okay, chalo, we move onwards, and an absolutely gem of a question, because this question is asking you Diels Alder reaction, but it is basically asking you aromaticity. So the question is, looks like it is on Diels Alder reaction, but no, it is on aromaticity. How is it on aromaticity guys? Because you know that in your Diels Alder reaction, the there is so many hetero-aromatic system over here. It is just that first one is not aromatic, it is your simple uh, uh, cyclopentadiene system over here. No, not aromaticity. Now the other three, 2, 3 and 4, all the other three, depending on their aromaticity, they are going to react with the maleic anhydride, with the phthalic anhydride, sorry. Okay, sorry, yeah. So which is going to be the best diene? Best diene is supposed to have minimum resonance energy, matlab ki minimum aromaticity and minimum resonance energy. That is why it is going to be the best diene. So order of resonance energy is 29 kilocalorie per mole. For pyrrole it is 22 or 23 kilocalorie per mole. For furan it is 16 to 17 kilocalorie per mole. So this is minimum, and the first one absolutely no aromaticity over here. So if I say the ease of reaction, if I say the ease of Diels Alder reaction would be best for 1, and then 2, and then 4, and then it is going to be 3. Now the question is asking you activation energy barrier. So activation energy barrier would be just opposite. So you are having 3, 4, 2 and 1 like this. C is your correct answer over here. Okay, so the question is based on aromaticity guys. Now another very important and very good question on the stereochemistry of iodolactonization, and this reaction iodolactonization gets asked in CSIR almost like every paper. So what you are going to do is, first of all guys, understand the stereochemistry of this beautiful reaction. So let's suppose that you are actually having the, at one point you have to suppose, right? So let's suppose that you are having the carboxylate group above the plane. Okay, and that is why, because the carboxylate is above, that is why you are adding the iodine from below. Let's say the double bond is going to attack over the iodine, and it is going to be electrophilic addition to the alkene. So what you are going to write is iodine below in this manner, and the carboxylic group above. O minus I'm writing on this side. So it is going to attack from above. Iodine is going to open up the bond and it stays below. It's a very, very simple reaction. If you are able to understand in this conformation, it's actually awesome. Otherwise, what you can do is you can write it in the chair form also. So for example, for this answer, it is your B. If you are interested in writing the chair conformation, that will be even more helpful. So let's say you are having the carboxylic acid group on the actual position like this, and let's say you have the iodonium ion formed below. So yes, if it is formed below, it is always going to the iodonium ion or bromonium ion or epoxide, everything they are going to be attacked in such a manner that they give the 1,2 diaxial product. So it is going to always be attacked on this carbon from the back, and this is going to be your product. Alright, so I is going to go below, and this is oxygen, this is your carbon, and this is connected right over here. So this is how the iodolactonization takes place. Answer is option B. Moving onwards, achiral stereoisomer is R. Matlab this is a MSQ question. Okay, is in R possible? So achiral stereoisomers, now it's actually very simple that here you are having this alene system over here. So both of these are hydrogens. Both of these groups will be perpendicular to each other, and a properly substituted alene is chiral. Similarly, a properly substituted biphenyl, which actually has bulky groups, so there is restricted rotation, that will also be chiral. So because of these bulky groups over here, there will be restricted rotations and it will be chiral once again. What about C and D, guys? So if you are writing option number C in Fischer projection, you will know that it is a acid like this. It is an acid like this over here. So either it could be written in this way, or it could be or it could be written in this way, all the OH on the same side. Yes, or it could be written in this way, 2 OH on the same side and one of the OH on the different side. This is your COH like this. So basically, ultimately what I mean to say is, in this form it is also meso, in this form it is meso, only in the last form it is your DL pair. So achiral stereoisomers are possible for C, and absolutely for D, if both the methyl groups are on the same side, there will be a sigma plane. So absolutely one of them is achiral. The cis is going to be achiral, the trans is going to be chiral. So C and D both are the correct answer. So moving on to our last question for today, the compounds which will have only 2 singlets in the proton NMR spectrum. Okay, you are searching for 2 singlets, but the ratio has to be 3:2. Okay, so let's see what happens is, guys, in option number A, if you see that there is a sigma plane of symmetry passing from here, you have one CH3, but this CH3 is going to give you one singlet with the intensity ratio 3 because there are 3 hydrogens. Other than that, you have 2 different types of protons. So this is your HA, this is your HB. In the benzene ring, you have 2 protons. So total 3 signals. 3 signals you get in option number A. In option number B, if you see that there is a sigma plane of symmetry passing from here, this is hydrogen A. Alright, this is hydrogen A, but then this is hydrogen number B on this carbon, another CH3 over here. So once again, this is going to have 3 signals. Looking at option number C. So if you want to write this conformation like this, then you can imagine a C2 axis perpendicular to the benzene ring. Or if you want to actually write the molecule like this, then it's actually very easy to see the sigma plane from here, as well as there is a sigma plane passing from here. So this methyl is absolutely same as this methyl, no doubt in that. And this hydrogen, this one hydrogen will be same as this one, same as this and this. So only one hydrogen in the aromatic region. Okay, and what will be the what will be the ratio of these methyls? There are 6 hydrogens from the methyl carbon because there are 2 of these, and there are 4 hydrogens from the aromatic ring. So it is, isn't it 3:2 that you wanted? Yes, it is 3:2, so C is our correct answer. Similarly, here we have 3 protons on the methyls, and this is your CH2 from the methylene group. So here also you have a sigma plane over here, and once again you are having 6 hydrogens from the methyl and 4 hydrogens from the methylene in the ratio 3:2. Only 2 signals, so C and D are your correct answer. Alright, so this is also an MSQ based on spectroscopy. So guys, I have taken some really important questions on organic and inorganic. If you want, you can check out the whole paper, guys. Yes, for all the students, for IIT JAM aspirants, I suggest you guys attempt all of your, practice all of your PYQs. For GATE aspirants, because now your MSQs are included, I hope that you are practicing enough questions. For CSIR NET aspirants, also guys, practice all of the questions that you get. Okay guys, so I will see you now in another video. And yes, if you are interested, then I would request you all to join me on Unacademy, because there are, as every month, there are a lot of free classes. And I want all of you to attend those free sessions of practice of concept, and you just have to use the code JagritiS to unlock free classes. And if you are subscribing to Unacademy Plus, the same code is going to fetch you a 10% discount. Okay, yes, so in the community post I will post about the free classes also. Alright guys, bye, we'll see you in a new video.